Hi, welcome to the SPDK Virtual Forum 2022 for PRC. My name's Jim Harris. I'm a principal software engineer at Intel and one of the SPDK core maintainers. I'd like to give you an update today on the SPDK state of the project. I'm going to cover this topic in three parts. We're going to start off with an update on the community as a whole, then dig into technology update. What are some of the features that we've added over this last year? And then looking forward, what are some of the things that you can expect from the community in the immediate future? First, what are some of the milestones over the last 12 months? We've moved to a 3 release per year cadence. So we had our last LTS, our long-term support release, back in January, our 22.01 release. And then we followed it up with releases in May and September. This is a slight difference from years past where we used to have 4 releases. We've moved to 3 to more closely match some of the other projects that we depend on, like DPDK, and also to lessen the burden of the release overhead for the project as a whole. We've also added a new core maintainer, Konrad Steiber from Intel. Konrad's based in Gdansk, Poland, has a long history of contributions to SPDK, including developing SMA, the storage management agent, which I'll talk about shortly. He's worked on NVMe over TCP improvements. He's worked on our tracing library. He's worked on the Intel VMD driver. We're really glad to have him as part of the core maintainer team. We also had our first SPDK community hackathons. We had one based in the US, and then we had another one for PRC community members, and these were mostly focused on the NVMe over Fabrics target, both VFIO user and TCP. There was quite a bit of focus on security and fuzzing. You're going to hear me talk more about that later. You're also going to hear Chunwan from Intel talk about this in one of her talks tomorrow. We've also added performance regression testing. So we've had quarterly or per release performance reports for SPDK for a very long time, several years. But more recently, Karl Atetsky and the SPDK benchmarking and performance team at Intel added automated nightly tests for performance regressions across several of our test cases. And so this helps us more quickly identify any performance regressions that pop in before running into them after the release goes and we do all the performance reports. So this has been really effective. We've found some issues we've been able to get fixed much more quickly. You can go to that link there to see all the detailed charts for those nightly tests. And then finally, we continue to have weekly community meetings. We have one that's more Euro-friendly time zone, and then one more for Asia. And one of the improvements that we've made to our overall process is to have one of these meetings every 4 weeks in Mandarin. So you can get details on that on the link there to see when those meetings are. So if that's something that you're interested, please check that out. Next, we like to look at patch statistics. So where are the patches coming from? How many are we getting? And those types of things. And so you can see over this most recent about 1 year release period since the 21.10 release, we've had 124 contributors, different contributors to SPDK from 35 companies. So this is huge. This is the highest number of contributors we've had on a yearly basis. And having them from 35 companies is also a record for the community. So we can see that we're continuing to draw a wider range of people into the community who are contributing and making the code base better and overall improving the project. We can see that the overall number of commits has gone down. It's gone down roughly just a little bit since last year. This was a shorter time window, only 11 months instead of 12 months. But we think that the what's in those commits is actually still pretty significant. So I think we used to have a lot of very small cleanup patches. We still have some of those, but I think if you look at those commits, you can see that it's a pretty extensive amount of work that's been done over this last year. One of the other metrics we like to look at is out of those commits, how many of them are coming from the top 10 overall contributors to the project. And we see this number continuing to come down, which is actually really good. It means that we're seeing more and more commits coming from a broader set of those contributors. And so it's really great to see this continuing to shrink. We're seeing more and more people who are contributing not just 1 or 2 patches every year, but actually contributing quite a bit more. We also like to take a look at our GitHub statistics, just what kind of traffic are we getting to the SPDK GitHub page. We continue to see this increasing. We're seeing about a 15% year-over-year improvement here. So now let's get to some of the more technology-based updates. So first, Storage Management Agent. This is a significant feature that's been added to SPDK, and it's all around simplifying IPU orchestration. You're going to hear a lot about IPUs tomorrow. We have several talks from June, from Andy Pei, from Zia Yang, who are going to talk about IPUs from different perspectives. So please listen to those talks. You're going to hear a lot more than just the brief update I'm going to give you here today. But the Storage Management Agent is all about abstracting the JSON RPC details from orchestration drivers. SPDK has a very rich and fully featured JSON RPC interface for doing configuration, but there is a lot of complexity. And so what we wanted to do was for these orchestration drivers, whether they're CSI node drivers or maybe third-party orchestration drivers, to simplify configuration of that IPU. So for example, any platform specifics, differences between different IPU or DPU types can be managed within the SMA agent, and then the third-party drivers or the CSI node drivers, or etc., they don't have to worry about those details. So currently the front end will support NVMe and Vert.io block. On the back end, it allows connecting to remote NVMe storage, and you're going to see a lot more work in this area over the next year, which I'll touch on later in my presentation. Next, NVMe multipath. This work started actually more than a year ago, but this is really fully complete now. Shuhei Matsumoto from NVIDIA has really been driving a lot of this work, and SPDK now supports 2 modes. First is multipath, which is based on asymmetric namespace access, ANA, which is defined by the NVMe spec. This allows the initiator to dynamically determine out of the paths that are available which one is preferred, which one is optimal. We also have a more manual path configuration called failover mode, which allows the administrator to explicitly configure paths, and then if one path fails, it will automatically fail over to the next one. We've also added a NVMe over Fabrics discovery service into the beat of NVMe module, which enables automatically discovering all these paths that are out there in the system. So this discovery service plus ANA makes this a very robust solution for having SPDK applications being able to connect and consume these NVMe over Fabrics clusters. Next, XNVMe. XNVMe is a open source project led by Samsung, and Simon Lund and Krishna from Samsung have been very involved in this work within SPDK. So XNVMe itself is all about enabling these new and existing Linux kernel storage interfaces. So, there was Linux AIO, IOU ring. More recently, there's what we call IOU ring command, and this is being able to use IOU ring but talking directly to the NVMe driver instead of going through the block layer. And so the work over the last year has been integrating this with SPDK. So having a SPDK BDEV module that can talk to XNVMe, and then giving SPDK the ability to use these new Linux kernel storage interfaces like IOU ring command. If you want to hear more about this, at the US Summit, there was a presentation on this by Simon, which has a lot more details. You can check out the SPDK blog to get links to that presentation. So next, the Excel framework. There's been a lot of work done on this over the last year. Paul Luce from Intel has been driving a lot of this, mostly around making this the primary interface for SPDK acceleration. So in the past, we had what we called our copy engine framework, which just offloaded data copies. But now it supports more things like CRC, memory fill, a lot more operations, and then on top of that, also pulling in things like crypto and compression, which typically we've talked directly to DPDK, compress dev, and crypto dev for that, but now we're pulling that under the Excel framework as well. There's been a lot of improvements to the IDXD driver, otherwise known as DSA. You'll hear Meng Jin talk about some of this SPDK DSA work later today in his talk. More work on module enumeration and selection. So, for example, the platform potentially may have multiple hardware engines and also a software sort of backup. And now you have the ability to sort of pick which ones you want to use. Maybe even though there's hardware available, you want to use software. That type of enumeration and selection is available. I talked about compression. So pulling in compression is another operation in the Excel framework. And also vectored CRC32. In SPDK, we have a lot of cases where we have maybe a bunch of 4 kilobyte data buffers that we need to perform CRC on. The CRC has to happen serially from a calculation point of view, but Ben Walker did some work with Greg Tucker from ISA-L to basically code up a way that we can do all the CRC32s for those 4K buffers in parallel, and in the end do some CRC math to be able to combine them. So we get a much better performant, a much more efficient way of doing CRC32 on these very large data buffers. Next, host FTL, flash translation layer. You'll hear Wayne Gao. He will talk more about this in his talk tomorrow, the cloud storage acceleration layer, which was merged into SPDK this year. And so for this host FTL, we basically take 3 main parts. We have a persistent write buffer. This is what aggregates all the writes that are coming in to the block device, and we write these to a high performance SSD. We have a logical to physical map. So basically keeping track of the logical blocks that have written by the user, where do they actually exist on the physical media. So this is persistent, byte addressable. It could be persistent memory. Currently, it's a high performance SSD typically with portions of it cached in DRAM. And then finally, the backing storage is a cost-optimized NAND tier. So we have RAID 5F listed here, where it's written out to basically a RAID device where you're always writing full stripes. The F stands for full. It doesn't have to be RAID 5F. You can write it to any block device on the back end, but this is really the preferred configuration. You'll hear Wayne talk more about this tomorrow. And more. There's a lot more things that we've covered. We can't cover all of them today. One is extending VFIO user, which was originally for NVMe, extending it for VirtIO. You'll hear Chong Pong talk about that in the next talk after mine. More about VDPA for storage. So this is something that Andy will talk more about tomorrow. So basically extending VDPA so that we can use it for things like VirtIO block. Ceph RBD optimization, so optimizing how SPDK leverages RAIDOS block devices. We have several talks on this tomorrow. You'll hear Kong Min from Intel and Yi Fan from Intel will both have talks. Also, Yue from IBM will be talking about some RBD related work. So if you have more interest in this area, please check those talks out tomorrow. More work around NVMe VFIO user optimizations, including things like interrupt coalescing, so reducing the number of interrupts that we inject into guest VMs, DAOS BDEV modules, DSA, IDXD transparent batching, blob store grow, trace optimizations, a lot of items here. Specifically the trace optimizations. I did a talk on this at the US Summit. That's another one that you can go and check out if you have more interest by checking out the SPDK blog. So next, looking forward, what are some of the things that we're going to see from the SPDK community over this next year or so? So a big one is orchestration. For those that aren't familiar, there's a new Linux Foundation project called OPI, the Open Programmable Infrastructure. And SPDK has been working very closely with OPI around things like SMA. So how do we create an orchestration framework that is going to work for the industry across these wide variety of IPUs and DPUs and SmartNICs? And so I think you can expect to see SPDK continuing to work closely in this area to really drive these industry standard interfaces. And a lot of them are going to be leveraging SPDK and SMA. We know that in this space, a lot of people are already using SPDK. We expect that to continue, and so SPDK is going to play a major role in this. Next is the Excel framework. So I mentioned crypto and compression. There's still work going on here. One of the major areas is that today we have BDEV modules for crypto, and we have a BDEV module for compression, and these talk directly to DPDK today. We want to change that. We want them to actually work through the Excel framework instead, have the Excel framework be the central API for any SPDK library that is consuming crypto or compression services. So that's going to be a major area of work over this next year. Another one is chaining. So there's a lot of cases where we want to be able to chain operations. We want to DMA and encrypt the data at the same time. So instead of copying the data into local memory and then compressing it there are hardware engines that can support encrypting it while it's being copied. And so this is really complex. Conrad Steiber has been driving some work here. There's actually a lot of people that are involved in discussions on this, but this is going to be something that's going to be, I think, really critical for having high performant solutions in this space, because the fewer round trips you can make to memory when doing these operations, the better. Everything just runs much more efficiently. So more hardware support. So adding support for more things on our hardware. For example, DSA has some compression capabilities, actually called IAA, having support for things like that. I think we can expect to see NVIDIA having more support for some of their hardware engines. I think you're going to see more of that over this next year. And then also more NVMe integration. So how do we take aspects of this and integrate it into more parts of NVMe? So for example, we've already integrated CRC offload into the transmit path for NVMe over TCP. Integrating this into the receive path as well. There's actually a number of areas here that we think we can improve NVMe over fabrics by doing these offloads, and that's going to be another area of work moving forward. So another big one on container storage. So you'll actually later today hear Xiaodong from Intel and Youngji from ByteDance talk more about this. But at a high level, there's a very common use case where you want to serve SPDK storage to local processes and containers. So not to a virtual machine, not to a remote node over a fabric, but to just a local process. And so today, the facilities, traditionally the facilities have not been great. There was NBD, called Network Block Device, which just was not performant. This works okay for maybe some very minor use cases, but it does not perform well. It is not meant for high performance and a very efficient code path like you would want for SPDK. Mostly what people have been doing in this space is NVMe over fabrics, but TCP loopback. And this is really the best option today. You can get pretty reasonable performance. We already know that on the kernel side, it's all multi-queue, so that's going to perform relatively well. But you do still have some of this TCP overhead. And so there's been a couple of more native solutions that have been integrated into the Linux kernel, which SPDK support is planned for the 23.01 release in January. So the first one is VDUs. This is I think like VDPA and user space. This is specifically what you will hear Xiaodong and Youngji talk about later. And it's doing this VirtIO block emulation in user space. So on the kernel side, you see VirtIO block devices, but on the target side, we actually have the SPDK target application servicing those VirtIO block requests. And then there's another solution that Red Hat has integrated called uBlock, UBLK. And this is another block MQ. This is all IOU ring based, which was integrated into Linux 6.0. So somewhat similar to VDUs, except this is actually a more generic. It's just called uBlock. It's not based on VirtIO or NVMe or anything like that. The SPDK target app communicates with the kernel to receive requests using an IOU ring-based protocol. And so this is another one that we think is going to, both of these we expect to see better performance and efficiency than what we see with NVMe over TCP loopback. And more. So we more RBD optimizations. Again, you'll hear more about this in the talks tomorrow. Some of the things, some of the further areas of improvements that we think we can make there. Blob Store external snapshots. Mike Gertz from NVIDIA talked about this at the US Summit. You can go and check out that presentation if you're interested. This is about today. The SPDK Blob Store and Logical Volumes, they support snapshots and clones. But in these cases, the snapshots and clones are all within the same Blob Store. And so what we want to be able to do is have a local a local clone, which just contains deltas, but the backing storage isn't another blob in the same blob store or another logical volume in the same logical volume store, but it is external. Maybe it's a remote NVMe namespace. And so Mike's doing work here to be able to support this in SPDK, cases where you have maybe images that are remote and you just store the deltas locally instead of having the entire image. More improvements around RAID. So I talked about RAID 5F. There's work for supporting RAID 1, but also having on-disk metadata. So today, all the RAID stuff in SPDK is effectively ephemeral, meaning you tell SPDK, here are the disks I want to put into the RAID volume, and they are not, there's no on-disk metadata. It's up to the administrator to make sure they configure those correctly. More fuzzing. So we're continuing to look at how do we fuzz interfaces like NVMe VFIO user. So we're presenting an NVMe interface to a guest VM. How do we fuzz that interface? So there's been a lot of work that's been happening already. As I mentioned, Chun will be talking more about this in her talk, but we think there's a lot more improvements that we can make here around register fuzzing, controller reset fuzzing. How do we combine these things together to just provide a more robust solution? More NVMe TCP optimizations. I think this work is going to continue for a long time. There's quite a bit of work happening. Ben Walker, Meng Jin are looking at ways to reduce the number of data copies that we have in the NVMe TCP path. So we always have this sort of trade-off where system call overhead can be high, and so we want to avoid system calls, but a lot of times with NVMe TCP, you're reading very small command structures, command capsules, or responses. And how do we amortize the cost of those? So today we have something called an SPDK pipe, which will pull a lot of data into a user space buffer, and then we'll copy out of there. They're looking at ways to optimize that so we can remove one of those data copies. Hot upgrade infrastructure. So how do we, with an SPDK process, be able to upgrade it in place? So this is, there's a lot of complexity here, of course, but this is, I think, really critical, especially for these IPU use cases where you want to be able to hot upgrade the SPDK application in place. And so a lot of this infrastructure we're starting to talk more about, and how do we get this in place. In some cases, we've seen some demos of some POCs where for certain use cases we can actually do this pretty effectively, but there's a lot more work that's needed here. And then finally, OpenSSF. So this is a Google project. It's basically around how do we measure ourselves as an open source project from a security perspective. And so there's a lot of different metrics here. I think overall SPDK is already doing pretty good when you look at some of the metrics and how we score. We're doing pretty well. There's more work that we can do here. One of the very interesting data points is Google and the OpenSSF team have developed a metric that they calculate for 100,000 open source projects that are on GitHub. Basically, how critical are those projects on a number of different metrics? How many different people are contributing? How long has a project been in existence? What's the activity on issues? Not just issues being filed, but how quickly they're being closed. And they take all these and they compute a criticality score. And when you look at all of the projects that they're evaluating, 100,000 projects, and this includes huge projects like the Linux kernel and Kubernetes, SPDK ranks number 346. So it's just one metric, but I think it really shows that this community is very vibrant. It's really critical. There's a lot of people that are using it, and we see that continuing moving forward. So thank you very much for listening. Hope that you found this informative. Please take advantage of the other talks today and tomorrow to learn more. And thank you, and enjoy the rest of the conference.